Hi there, I'm Mr. Sand, and now I'm going to talk about transition metals because transition metals, those transition metals, they can get really, really tricky. So, let's start this sucker. Transition metals to start off with, they're this middle kind of pinkish, fleshy looking color in the middle. I don't know. That's kind of this boring pink color in the middle here. Those are the transition metals. From here, from scandium all the way over to zinc and down to Copernicum, and of course, all of these lanthanide and actinide series over here. We won't get into that hardly at all, but they're there. They're just kind of like, think of these two elements right here, here and here, as being folded out, and you've got all of these elements that are residing in these two places. Okay, so what happens if you've got this metal, which is a transition metal, and it's bonded to something that's a nonmetal, like fluorine, let's say like iron and fluorine? Well, the strange thing about transition metals is that they don't have a set number of electrons that they give away. Sometimes they give away one electron for an ionic bond, and that makes them the most stable that they can be. Sometimes there's other times in which they give away two or three or four or five or even six electrons, and that makes them perfectly stable as well. It's all about the kind of stability between them and the other element that they're bonded with. That's what determines how many electrons it gives away. But just looking at the element, you can't tell, iron, that's going to give off one electron. No, 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 you cannot tell that. There's several ways it can give off electrons. It can give off two or three or four and all be stable. So it's not like beryllium, where beryllium, it's going to give away two electrons. You can just look at it and know it's in the second group. It's going to give away two valence electrons to whatever nonmetal it's bonded with, but not these pinkish color elements in the middle. You don't know. So we have to name them in a different way. Being chemists, we have to be more specific. So I'm going to do it right now. I'm going to use iron as my example. Fe is the symbol for iron. So let's start off with Fe. And let's say it's bonded with, here's a formula. The formula is Fe. And it's bonded with oxygen. Haha. Its name. I'm going to tell you the answer, and then you're going to tell me what the heck's going on here. It's iron, parentheses, Roman numeral 2, oxide. Iron 2 oxide. Whoa, crazy. But now I'm going to give you a different formula. Fe2O. What? This is iron, parentheses, Roman numeral 1 oxide. What's different between these two cases? Well, here, let's just think about what's going on between these two atoms. The iron and the oxygen. Here are the valence electrons for oxygen. There's 6, which means that there's 2 holes that need to be filled around oxygen. It needs those 2 electrons. Iron 2 oxide. If you have one iron atom and one oxygen atom, that must mean that iron has given away 2 electrons. So now oxygen's fully satisfied and iron's fully satisfied. Iron's given away 2 electrons here. So that's why this is called iron 2 oxide. That's cool. Now let's look at Fe2O. Well, that means that there are 2. It's a different scenario now. So I'm going to use a different color. I'm going to use the red. There are 2 iron atoms, and there is 1 oxygen atom. So I'll draw all the electrons around oxygen and the holes it needs to be filled. So there's 2 holes that need to be filled around oxygen. Fe2O. So that must mean that what does that have to mean? That means that each of these iron atoms is contributing an electron to this oxygen. That's the only way it could work. Because it only has two, you can think of them as two vacancies for these electrons. And so if it has two iron atoms around, it must mean that each of those iron atoms are contributing something, because it wouldn't just be, this one wouldn't just be hanging out on its own. For an ionic bond, it needs to have given some electron. So it has to at least give one, each one of these. So this is iron 1 oxide. Okay, so this Roman numeral in the middle here means that iron is giving 1 electron. And over here, that 2 means giving 2 electrons. Oxygen's still receiving 2 electrons, both cases. But here, the iron is giving 2 electrons. Here, the iron is giving 1 electron. That's what this name means. That's what that name means. And these formulas over here correspond with it. Okay, so let's do some problems. I'm going to do a problem right now. Let me actually use the same examples here, but I'm going to use a different way of approaching these problems. I'm going to give you the formula, and I want you to figure out what the name is. So the formula is FeO, and we know that it's iron 2 oxide, but let's see if we can figure out how we got there just from this formula. Okay, so FeO. First thing I would do is I would draw these, I would just write out Fe and O. Okay, so I know that oxygen takes, well, first of all, hold on. Okay, so I know that oxygen takes 2. We don't know how much iron takes in this case. Okay, this might be a little bit trickier for this example. So oxygen takes 2, and we don't know how much iron takes in this case. But we do know that this number down below here, even though it doesn't have a number, we know that it really means 1 and 1. So let's see over here. This is not a good example to start off with. Let's use a different example to start off with. That's not the best because it doesn't work as seamlessly as I thought it would. Okay, let's use a different example. Right. Let's choose any other. Let's use nickel. It doesn't really matter. All right, nickel. And let's say nickel. And let's do nickel 2 and let's do fluorine and 2. Okay, Ni2